On August 18th, 2026, we know something that was completely impossible to know just 6 months ago. There is an entire galaxy out there, a real confirmed galaxy, that is made of 99% dark matter. Not mostly dark matter, not mostly invisible, 99%. Scientists found it in February 2026, and the way they found it broke every rule about how galaxies are supposed to be discovered. Nobody saw it with light, nobody detected it with radio waves. There were no glowing stars pointing to it. There was almost nothing there at all. And yet it exists, floating 300 million light years away, a ghost galaxy full of mass that the universe simply refuses to show us. This is the story of Euclid, the telescope that is rewriting everything we thought we understood about what the universe is actually made of. And what it has found, in just the last few months alone, is going to leave you questioning everything. Before we can understand what makes this discovery so extraordinary, you need to understand what dark matter actually is, because most explanations make it sound more mysterious than it needs to be. Here is the simplest version. When scientists look at galaxies spinning, they see a problem. The stars at the edges of galaxies are moving too fast. Under normal physics, with only the visible mass inside a galaxy creating gravity, those outer stars should fly off into space. They do not. Something is holding them. Something with mass and gravity that we cannot see, cannot touch, and cannot detect with any instrument that picks up light. Scientists called it dark matter, and when they ran the numbers on the entire observable universe, they found that the ordinary matter you and I are made of, every atom, every star, every planet, adds up to only 5% of the total mass energy content of the universe. Dark matter makes up another 27%. The remaining 68% is something even stranger called dark energy, which is responsible for the universe expanding at an accelerating rate. That means 95% of everything that exists is invisible to every telescope ever built. We know it is there because of what it does to the things we can see, but what it actually is, nobody knows. This is the central mystery of modern cosmology, and it is exactly the mystery that the Euclid Space Telescope was built to attack. Euclid launched on July 1st, 2023 from Cape Canaveral, Florida. It took 23 countries, 80 companies, 300 research institutes, and 3,500 people to build. It traveled 1.5 million kilometers from Earth to a gravitational sweet spot called Lagrange Point 2, where it now sits alongside the James Webb and Gaia telescopes, permanently positioned with the Sun, Moon, and Earth behind it so that none of them ever interfere with its view. From there, it is conducting a 6-year survey of roughly a third of the entire night sky, imaging more than 1.5 billion galaxies, some of them as far as 10 billion light years away. Its goal is to create a three-dimensional map of the universe spanning 10 billion years of cosmic history, looking specifically for the fingerprints of dark matter and dark energy in the structure of everything it sees. No telescope has ever attempted anything at this scale. And in the roughly 2.5 years since it started returning serious science data, it has already overturned things that astronomers thought were settled. What makes Euclid different from every other telescope comes down to 3 things. First, its wide-angle lens captures more sky at once than any telescope in history. In one observation, it records vast cosmic structures, while simultaneously capturing precise details of individual galaxies. It has 4 times the resolution of ground-based surveys in visible light, and 15 times the sensitivity in near-infrared wavelengths. It can detect objects hundreds of times fainter than the Gaia telescope can see. Second, it measures tiny distortions in galaxy shapes caused by dark matter bending light through a phenomenon called gravitational lensing. Every clump of dark matter between us and a distant galaxy bends the path of that galaxy's light ever so slightly, distorting its shape in ways that can be measured and mapped. By doing this across billions of galaxies, Euclid can reveal where dark matter is concentrated across the entire observable universe. Third, it does all of this at the same time, combining a wide panoramic view with the precision of a surgical instrument. It is both the widest and the sharpest survey telescope ever put into space simultaneously. Because of that combination, it has been finding things that more focused, more specialized telescopes simply could not see. The first truly jaw-dropping result came in February 2026. Using Euclid data alongside images from the Hubble Space Telescope and the ground-based Subaru telescope in Hawaii, astronomers confirmed the existence of a galaxy unlike anything ever recorded. It is called CDG2, which stands for Candidate Dark Galaxy 2. It is located 300 million light years from Earth in the Perseus galaxy cluster, and when scientists analyzed its composition, they reached a conclusion that barely seems possible. Approximately 99% of CDG2 is dark matter. The remaining 1% is ordinary matter, stars, gas, anything that actually emits light, and it is so sparse that the galaxy's total luminosity is equivalent to roughly 1 million suns. Our Milky Way, by comparison, shines with the light of hundreds of billions of suns. CDG2 is not just faint, it It is almost completely dark, and the way it was found makes this discovery even more remarkable than the galaxy itself. Nobody spotted CDG2 by looking for it directly. There was almost nothing to see. Instead, the team led by David Lee at the University of Toronto was searching for tight groupings of globular clusters, dense spherical collections of very old stars that typically orbit normal galaxies. The idea was that globular clusters sometimes act as markers for galaxies that are too faint to detect on their own. Using statistical methods on Hubble images of the Perseus cluster, they identified 10 extremely dim galaxies. 2 appeared unusual. CDG2 stood out immediately because it seemed to have only 4 globular clusters surrounding it, compared to the 150 plus that orbit the Milky Way. 4. That tiny handful of star groups was essentially all there was of CDG2 in terms of visible light. But those 4 clusters were a clue that something massive was there, invisible and waiting. To confirm it, the team turned to Euclid, and what Euclid revealed settled the question completely. Francine Marleau from the University of Innsbruck said it directly. The Euclid data clearly confirmed the presence of extremely faint diffuse light of CDG2, revealing the galaxy behind the globular clusters for the first time. Euclid caught the faintest imaginable glow surrounding those 4 star clusters, the ghostly signature of a galaxy whose individual stars are too dim to resolve individually, but collectively produce just enough light to be real. This is the first galaxy in history detected solely through its globular cluster population. We found a galaxy not by seeing it, but by finding a few tiny stars and inferring that something enormous and invisible had to be holding them together, and that something turned out to be almost pure dark matter. This discovery matters beyond the headline number. In a typical galaxy, dark matter outweighs ordinary matter by roughly 5 to 1. CDG2 flips that ratio to something like 99 to 1. That extreme imbalance gives scientists something they have never had before: a laboratory where dark matter is essentially undiluted. Almost none of the messy ordinary matter that normally complicates measurements of dark matter is present. Scientists believe CDG2's extreme nature may be explained by its aggressive environment inside the Perseus cluster. The cluster's gravity and the dynamics of nearby galaxies may have stripped away most of the ordinary matter over billions of years, leaving behind the dark matter halo and almost nothing else. Studying CDG2 is now one of the highest priorities in dark matter research, precisely because it offers a chance to probe what dark matter does when it is not mixed up with stars and gas and all the ordinary physics we already understand. And researchers immediately pointed out that CDG2's discovery raises an even bigger question about its possible twin, CDG1. If CDG2 is this extreme, CDG1 may be even more dark matter dominated, potentially a galaxy with almost no stars formed at all outside its globular clusters, if it even has those. The universe may be full of galaxies we have never seen, floating in the darkness, made almost entirely of something we cannot yet explain. But Euclid did not stop there. In May 2026, scientists published a first demonstration of something that the entire Euclid mission was engineered to do: detecting the invisible architecture of dark matter through weak gravitational lensing at cosmological scale. This is the subtler and scientifically more powerful version of the gravitational lensing concept. Instead of a single galaxy bending light from one galaxy behind it into a dramatic Einstein ring, weak gravitational lensing involves enormous clusters of dark matter spread across millions of light years, bending the light from millions of background galaxies by tiny amounts. Those tiny distortions are statistically invisible in any single galaxy. But when you look at millions of galaxies together and search for patterns in how their shapes deviate from what you would expect by chance, the dark matter concentrations reveal themselves. Euclid successfully demonstrated it can do exactly this at the scale needed to map dark matter across a meaningful chunk of the universe. The full cosmology results from this technique are expected in 2027, and scientists working on the project have described the anticipation building in the astronomy community as unlike anything they have experienced in their careers. In June 2026, Euclid turned to something much closer to home, and the result was the most detailed image of the center of our own Milky Way galaxy ever captured in visible light. This image, released on June 24, 2026 as Euclid's Quick Data Release 2, was assembled from observations taken in just 26 hours, a single day of work. Yet it captured tens of millions of stars in a mosaic of detail that no previous telescope had achieved at this scale. What makes this image scientifically explosive is not just what it shows now, but what it makes possible in the future. When NASA's Roman Space Telescope later observes the same region of the sky and detects a microlensing event, the brief brightening of a star caused by a planet passing in front of it and gravitationally bending the star's light toward Earth, scientists will be able to compare that brightening against Euclid's baseline image of just the star with no planet in front of it. That comparison immediately tells them the planet's mass and orbital characteristics. Euclid essentially created a reference library for planet hunting at the galactic center, a region so crowded with stars that it was previously almost impossible to study systematically. Scientists estimate that thousands of planets are hiding in that image right now, waiting to be identified when the Roman telescope begins its observations. And then, just 6 weeks ago on July the 6th, 2026, Euclid delivered what may be its most purely astonishing result so far. The telescope discovered 31 of the oldest quasars ever found. Not old, ancient, cosmically ancient. 2 of them set new records as the most distant quasars ever observed in the history of astronomy. Their names are Euclid J72902, 75216641, and Euclid J1125308, 55054323. And they have redshifts of 7.77 and 7.69, respectively. Redshift is the measure of how much a galaxy's light has been stretched by the expansion of the universe as that light traveled toward us. The higher the redshift, the further away the object. And the further back in time we are looking, a redshift of 7.77 means we are seeing this quasar as it existed when the universe was only 670 million years old. The universe today is 13.8 billion years old. We are looking at an object from when the universe was 5% of its current age. The light Euclid caught from these quasars has been traveling through space for more than 13 billion years and has only just arrived. This beats the previous record for the oldest known quasar, which was set in 2021 at a redshift of 7.64, by about 20 million additional years of cosmic time. But what makes this discovery unsettling to physicists is not just the age, it is what these quasars are. A quasar is the blazing core of an early galaxy, lit by a supermassive black hole that is actively swallowing gas at a rate so extreme that the energy released outshines the entire rest of the galaxy by hundreds or thousands of times. The quasars Euclid found were each shining with the light of roughly 1 trillion suns, and each of those quasars was powered by a black hole with a mass approximately 1 billion times the mass of our sun. That is the problem. Building a black hole 1 billion times the mass of the sun takes an enormous amount of time and infalling material. Physics sets limits on how fast a black hole can grow. And yet, here are black holes with that mass, already fully formed, when the universe was less than 700 million years old. There was not enough time under our current understanding of how black holes grow for these objects to exist at the size they are. Something about the earliest universe allowed black holes to grow faster than our models say is possible, or they formed from seeds far larger than anything we have directly observed. Every one of those 31 ancient quasars is a challenge to the standard model of early cosmic structure formation, and Euclid found 31 of them in one survey sweep that took a fraction of the time it took previous missions to find a handful. Lead researcher Daming Yang from Leiden University in the Netherlands described it plainly. He said that before Euclid, they could only find a handful of the very brightest ancient quasars. Euclid lets researchers search far more efficiently across enormous areas of sky to capture much fainter light. It is a unique tool for quasar hunting, and nothing else comes close. It took scientists a decade of painstaking work using dedicated telescopes to identify about 10 quasars from the universe's first 770 million years. Euclid found 12 more in a single year, plus another 19 at slightly closer distances, all in the course of normal survey operations that were primarily aimed at mapping dark matter. The ancient quasars were essentially a side product of a telescope doing something else, and the entire haul of 31 roughly doubles the number of known quasars from that early stretch of cosmic history. The full cosmology data release is still coming. If this is what Euclid produces as a side effect of its main mission, while covering only a portion of the sky, what happens when the full survey is complete? To process everything Euclid is seeing, scientists are deploying artificial intelligence at a scale that is itself remarkable. The data volumes involved are measured in petabytes, hundreds of petabytes. A single petabyte is 1,000 terabytes, and a terabyte is already far larger than most home computers store. Euclid sends back approximately 100 gigabytes of data every single day. Over 6 years, the total archive will be one of the largest scientific datasets in history. No human team could search it manually for Einstein rings, weak lensing signals, faint dwarf galaxies, dark galaxy candidates, or ancient quasars. Machine learning systems trained on known examples of each phenomenon are doing that searching, flagging candidates that are then reviewed and verified by the thousands of scientists working on the mission. When astronomers used a similar AI approach on data from the Very Large Telescope in Chile, the system identified 56 gravitational lens candidates automatically. A citizen science project in Japan had 10,000 volunteers identified 20,000 galaxies by hand, then trained an AI on those results, and the AI found 410,000 more galaxies in the same dataset with 98% accuracy. What is happening with Euclid is that same process at a scale orders of magnitude larger, and the results are already arriving faster than the scientific community can fully absorb. By the time Euclid completes its 6-year mission in 2029, it will have covered roughly a third of the entire night sky. Right now, in August 2026, it has completed approximately 35% of its target survey area. With 4 years still to go, it has already found a galaxy made almost entirely of dark matter, demonstrated the ability to map dark matter across cosmic scales using weak gravitational lensing, created the most detailed map of our galactic center in history, discovered the oldest quasars ever recorded, and produced datasets that are rewriting our understanding of how the early universe assembled itself. Every single one of those results arrived in roughly the last year of operation. The survey is still barely beginning. What Euclid is really doing, underneath all of these individual discoveries, is building the evidence base needed to finally answer a question that has haunted physics and astronomy for a century. What is the universe actually made of? We know the answer is mostly dark matter and dark energy. We know they exist because removing them from our equations makes everything fall apart. The rotation of galaxies, the formation of large-scale structure, the acceleration of cosmic expansion, none of it works without the 95% we cannot see. But knowing something exists and understanding what it is are completely different things. Dark matter could be particles that interact with ordinary matter only through gravity, particles so lightweight or so weakly interacting that every detector built to find them has come up empty. Dark energy could be a property of empty space itself, a constant energy density that grows as the universe expands, steadily overwhelming gravity on the largest scales. Or it could be something stranger, a dynamic field that changes over time, sometimes stronger and sometimes weaker, the fifth fundamental force of existence that some physicists have called quintessence. Euclid cannot directly detect dark matter particles or dark energy fields. What it can do is map the effects of both on the three-dimensional structure of the universe across 10 billion years of history. If dark energy has changed over time, that change will show up in the way cosmic structure evolved differently at different epochs. If dark matter clusters in specific ways that our particle physics models predict, that pattern will appear in the lensing maps. The full cosmology results expected in 2027 will be the most complete test of our models of both dark matter and dark energy ever attempted. Right now, from 1.5 million kilometers away, Euclid is staring at the sky in its quiet way, collecting light that has been traveling toward us for billions of years. Some of that light left its source before the Earth existed. Some of it was emitted by galaxies that have long since merged, evolved, or gone dark. Every photon that lands on Euclid's detectors carries information about the structure of the cosmos at the moment it was emitted, and about every clump of matter it passed near on its journey to us. Piece by piece, discovery by discovery, that information is being assembled into the most comprehensive portrait of the invisible universe ever attempted. A galaxy made of 99% dark matter. Quasars from 5% of the universe's age. The center of our own galaxy mapped in a single day. The architecture of dark matter traced across hundreds of millions of light years. And 4 more years still to come. Whatever is out there in the dark, Euclid is going to find it. If this kind of content is what you want to see more of, hit subscribe and turn on notifications. I cover the biggest discoveries in space science as they happen. And right now, with Euclid in full operation, things are happening fast. Drop a comment below. Which of Euclid's discoveries so far blew your mind the most? I read every single one, and I will see you in the next video.